And so don't forget we have the exam on Friday, 1 week from today. We have a health session today at 12:55, and I'll have a final open stack to sum it up. Hopefully the test will be tomorrow morning. It'll be due like Wednesday or Thursday of next week. It'll be on dissertation stuff that we're going to do. We are going to move into chapter 8, but let's not put it on anything. Is that good? Yeah. And so we'll put it on the next week. Okay, but we're going to get into chapter 8. And it's sort of related to chapter 7, but let's just the top 6. Okay? Any news for this weekend? Any big events? Studying for what? For my test, it's not until Friday. So that's good because you don't want to put it off, huh? Yeah, you're right. Right. 20 minutes a day, that's right. So, all right. Any other? I think it's supposed to be nice weather. It's going to get cold. Any other big events? I mean, y'all like the most boring. Y'all never do anything. All right. This weekend we have sort of a normal Saturday. Like a normal Saturday is we go for a bike ride, and then we go shopping, like grocery shopping, and then we go to the library. And then, like all afternoon, we just sort of lay around the house and do nothing. And Sunday, I'm preaching on Sunday at a little church in Houma. And then on Sunday afternoon, we'll just lay around for the day. That's about it. Ethan? What are the jambalaya tickets for? SAE. Okay. You're an SAE? Yeah. If you want one, you can see Ethan. Okay? So y'all don't like the tack with the shirt? It doesn't work.
It would make more sense if it was only white and black shirt.
Yeah, I know. The thing is, like I got this shirt, and Claire sold me this shirt at stage, and then I got home and I didn't have a tie to wear with it, so you get what you get. I have a black tie, but it's from many, many years ago, and it's like a navy tie, like not the color, but like the U.S. Navy, and it's kind of short, because they usually tuck those ties in.
You don't have to wear a tie.
Let's do this question. Okay, so let's do this. And then we'll do some more practice questions from chapter 7. And then we'll move on to chapter 8. Remember what we talked about, that in rotation, your centripetal force, it's not a new force, it's a force that's already there. And so we talked about the salad spinner deal at the fireman's fair, and a truck going around a curved path. And that's what we have here. We have a truck going around a curve. And when I have that, I want to ask myself, what is the force that keeps this object on the road, this truck? And then that's going to be our centripetal force. What is the force that forces this truck into this circular path? I'm going to give you a little bit of a head start. I'm going to jump in and help you and sort of, it's a little bit with it. I want to jump in and give you a little help. This is actually a homework problem, or from the extra practice problems in your workbook. So I have two situations here. I have the truck going around a curve with a 120-meter radius, and then the truck going around a sharper curve with a 75-meter radius. And I know that the maximum speed on this curve is 25 meters per second. And then I want to know what is the maximum speed on this curve. And so there are a couple ways you can do this. One way is you can figure out what is the coefficient of static friction. Because the coefficient of static friction on this road is going to be exactly the same on this road. Just because you make your curve sharper doesn't mean that it changes your friction. Right? So we can first find out what our coefficient of static friction is. Now, I know that my centripetal force, in this case, is my static frictional force. Right? The static frictional force plays the role of the centripetal force. And so that's going to be mv squared over r. That's Newton's second law for our centripetal force. How do I find my static frictional force? It's what? I recall Fn mu, right. So it's mu times Fn. But remember, when something's on a horizontal surface, I'm just going to replace that Fn with mg. Okay, and then I can use that to solve for mu. My coefficient of static friction. Then I can do the same thing for my 75 meter, except now I know my coefficient of static friction. I can say Fs is equal to Fc, but then solve for the speed instead of the coefficient. All right, I shall wrap that up. All right, let's stop in about 20 seconds. Just guess if you're not sure, okay? Stop at 5 minutes. Yeah, about 35 of you have it right. So I'm going to stop at 5 minutes. Okay, A is the right answer. So we would solve for mu, and here, notice that my m's cancel out, and then I can solve for mu. It's going to be v squared over gr. The v is going to be 25 meters per second squared, divided by 10 times r, which is 120 meters, and that works out to be 0.52. Then I can figure out what is my mu speed. And so I say mu mg equals mv squared over r. Get rid of my m's. V then is square root of mu gr. Using the mu, the coefficient here, and using the new radius of 75 meters, then I find the speed. It is going to be 20 meters per second. That's actually how they calculate those speeds. They figure out what is the measure of the friction on these roads in certain conditions, and then they figure out what is the is that what you need, Gavin? And then they figure out what is the maximum speed that you can do on these. Notice what's not dependent upon this, that you don't need the mass of the truck. So it doesn't matter on these curves as you go around the curves. It doesn't matter what the mass of your car is, because it falls out and the mass cancels out. So your frictional force, at least on a flat curve, will be the same for a little Miata and a big old Ford F-150. Okay? Never mind. We're actually good. Right, let's look at the next one. Here you're not looking for the force, but you're looking for the acceleration. Be careful your units here. Notice that this is in revolutions per second. All right, let's do about 15 or 20 more seconds. Feel free to ask your neighbor, though we are literally all over the board. I can't even tell what the right answer is by looking at your answers. So. But feel free to ask your neighbor. They might not be right. Watch your units. You're never going to go wrong converting to radians. You'll need to convert your angular speed to a linear speed, unless you remember that alternate expression we have for centripetal acceleration. All right, I'm going to stop at 208, or 210, I'll say. There's 5 more seconds, guess if you don't know. Okay, it is E. So 22 of you got the right answer. So first of all, I want to know the acceleration. There are a couple different kinds of acceleration. There's our linear or tangential acceleration. But if I look at this, it says that it's moving with constant angular speed. That means that alpha is equal to 0 radians per second squared. Remember, alpha, that's our angular acceleration. So alpha is equal to 0. So I'm not looking for a tangential acceleration because AT, I'll call AT for tangential, which is equal to alpha times r. That's also equal to 0. So that acceleration is not there. The only other acceleration that I have is my centripetal acceleration, AC, and it's equal to v squared over r. I could do this a couple different ways. I could figure out what is the speed, v, or I can remember that there's an alternate expression for this, which is omega squared r. This isn't in your equation sheet. Let me show you how we get that. We just say that v is equal to omega times r. Since a is equal to v squared over r, this is omega r squared over r, which is omega squared r. And so that's where that comes from. So this will give me my centripetal acceleration. However, the units are wrong on this. No, they're not. No, never mind. No, they're not. They're okay. So 5 revolutions per second. I need to convert that into radians. In 1 revolution, there are 2 pi radians. So that gives me 10 pi radians. And I just kept the pi in there and put it in the answer. And so now I have 10 pi squared times 0.1. 10 squared is 100. 100 times 0.1 is 10. So it works out to be 10 pi squared. And the units of this are in meters per second. Okay? Or excuse me, not meters per second. Meters per second squared. Okay, folks? We'll do some more. We'll do some more practice from this. All right. Let's take a look at some more. I think that's the last here. Let's try number 24 to start. All right, and then after we do number 24, yeah, let's do 24. And then we'll do 21. So start with 24. But if you finish 24, you can go on to 21. I'm going to look at 24 here. look at your equation sheet, a lot of these equations are coming around that. This is one of your kinematics problems. All right, let's try to wrap up in about 20 seconds. Do this 24, go on to the number 21 on the left. I'm going to stop at 3 minutes. 10 more seconds. 10 more seconds. All right, I think D is right. Let's take a look. So, with these, as in Chapter 2, and sort of the difficulty of these are not quite as what we got into in Chapter 2. They're going to be largely just sort of picking out the variables that you find and knowing how to work with them. So you want to write down everything that you know here. We know that the initial speed, that's omega naught, is equal to 0.5 radians per second. The time is 7 seconds, and it accelerates at a rate of 0.04 radians per second squared. So that's alpha. It's 0.04 radians per second squared. Part of these problems are just knowing which number goes with which variable, because we got different variables now, and they're all Greek, right? So those are sometimes hard just to remember. You might want to write them out on a note card or something. A is the same as alpha, V is omega, X is theta, and maybe even write the units next to them and just paste it to your bathroom mirror or whatever, or wherever you look at it. Okay? Just to help you familiarize yourself with those. Now I want to know the angular displacement, theta. Theta is equal to omega naught t plus 1/2 alpha t squared. And in these problems, when you're doing these kinematics problems, you can have it either in radians or revolutions or degrees. It doesn't really matter. Like if I were to have all these in revolutions per second and revolutions per second squared, then the answer would just come out to be in revolutions. But here everything's in radians. You'll never go wrong converting everything to radians. Sometimes you might go wrong not converting to radians. Because all the other problems that we did, centripetal force, and when we get into torques and all that stuff, you'll need to always convert those into radians. So unless you're certain that you may or may not need to convert to radians, then I would just do it. And there will be some problems where I'll give you the quantities in revolutions or degrees per second. Okay? All right. So, but here everything's in radians. So I have 0.5 times 7 plus 1/2 alpha is 0.04 times 7 squared. And what do we say that was? Is it D? Yeah. So 4.48 radians. All right. Have y'all done 21? Let's do 21. What is the displacement of a clock between midnight and 3 a.m.? The displacement of the hour hand. Finish this one, go on to 22, okay? Go on and do 22. And then do 23 if you finish that one. We'll do 21, 2, and 3. I'm going to stop this at 105. 105. Okay, good. A is right. I know that a clockwise is negative, so it gets rid of some of these. And then I want to go from midnight to 3 a.m. Midnight is here, 3 a.m. is here, so I'm going in this direction, and that's going to be minus pi over 2 radians. All right, let's do number 22. If you finish 22, go on with 23. All right, let's stop at 110 or 115. Feel free to ask your neighbor. You're all doing pretty well, so ask almost anybody around you. They'll probably shoot you straight. All right, I'll stop at 125. 125. Okay, good. A is right. Here, I have this Ferris wheel, folks going around this Ferris wheel. And I just want to know what is the centripetal acceleration. So I have somebody sitting here. I know that the angular speed, omega, is, was it 0.5? Is that 0.5? Yeah, it's 0.5 radians per second. And I know that the radius is 12 meters. And so I can calculate that centripetal acceleration is going to be either v squared over r. And if you do that, you're going to have to figure out what v is. V is equal to omega r. So that's going to be omega times 12, or 6 meters per second. So it's going to be 6 meters per second squared divided by 12. That's 36 over 12, which is going to be 3. Or you could say AC is equal to omega squared r, which is going to be 0.5 squared times 12, which is also 3. A quarter of 12 is 3. Okay? All right. Did I say 23 as well? Some of y'all done 23? Let's try that one out. Here I have a stone and I'm swinging it overhead, and I want to know what is the maximum speed, because the string will break if I get a certain force on it. All right, let's go about 15 more seconds. Stop at 110, 110. Okay, good. B is right. So I know that the centripetal force is the tension. So this is one of those cases where my centripetal force is being provided by another force. In fact, that's always the case. The centripetal force is just some other force in the system. And in this case, that force is the tension. And so I know that my tension can exceed 80 newtons, and that my centripetal force is mv squared over r. So here I would solve for v, because that's what I'm looking for, which is going to be the square root of 80 times r divided by m, which is 80 times 2 divided by 10, which is equal to 4. So B is the right answer. Square root of 16 is B. Okay? All right. Hey, do y'all know what the great thing about Switzerland is? I don't know, but the flag's a big plus. Okay, let's see what else we got. I think I stop with that. Today in the help session, we'll be going over mainly, I think, momentum and energy. But if the folks that come, if y'all want to do rotation too, we can do that. But we shall have another help session next week. I don't know, let's do it on Friday. How about that at 12:55? No, that doesn't work because your exam is on Friday. We'll have it probably on Thursday at 2 or 3 o'clock. I'll send out a note about it later. Okay? I do want to address one thing. This isn't really for the exam, it's just sort of for you people that it's important for. But let's go back to where we have a blank page. At the end of that chapter 7. So let's imagine that Ferris wheel. Right? The Ferris wheel, it goes around at a certain omega. And the Ferris wheel, like, first imagine that you're not on just any old normal Ferris wheel, but you get on the Ferris wheel and then something breaks. And that starts going around really, really fast. Okay? When you come to the bottom of it, you're going to get pushed down into your seat, right? Like, it's going to feel like you're pushed into your seat. But what's going to happen when you come up to the top of the Ferris wheel? You're going to sort of lift up. It's kind of like when you also go across hills in your car. We don't have many hills around here. But if you go across your hills, when you go in your car, when you come to the top of the car, you sort of lift up out of your seat. Top of the hill, you lift up out of your seat. When you come to the bottom of the hill, you get pushed down into your seat. Or it feels that way anyway. So let's imagine this mad runaway Ferris wheel. I can draw force diagrams. And again, this isn't really for your test. It's important, but I'm not going to test you on this type of material. When I'm at the bottom, I can draw the forces that are acting on it. I have the force weight, and I have the normal force. And these two forces combined will act as our centripetal force. I actually have two forces that will act as a centripetal force. And so I can write my Newton's second law. Sum of the forces equals mass times acceleration. But it's not accelerating tangentially. It's only accelerating with a centripetal acceleration. And so the sum of my forces is going to be Fn minus Fw equals to MAC. And so here, if I wanted to calculate my Fn would equal to MAC plus Fw. Now MAC is equal to, or AC rather, is equal to omega squared r. So it's set by how fast the Ferris wheel is spinning around. This is at the bottom. But think about up at the top. Up at the top, I have a normal force in this direction, and my weight in this direction. And if I write at the top, I have it looks like this. I have Fn minus Fw equals MAC. But in this case, what is the direction of my centripetal acceleration? Always, this is important for your test, always, what is the direction of your centripetal acceleration? Is it left or right or up or down? It's always towards the center, right? So the centripetal acceleration is always towards the center of your motion. And so in this case, my centripetal acceleration is down. Over here, my centripetal acceleration was up, which is why this was a positive value. But now I have a negative value here. And so keeping that as negative, if I want to calculate Fn, then I have Fn is equal to Fw minus MAC. We've done this before. We've done vector diagrams and we've done applications of Newton's second law. But you can do it also with rotation. And then so in this case, this is Fn bottom, this is Fn top. Then you see that the normal force at the bottom is bigger, right? That's where you're getting, it feels like you're being pushed down into your seat. Really the seat is pushing up on you harder. And at the top, the normal force is smaller. You sort of come out of your seat a little bit because that normal force is smaller. Okay? Again, you're not going to have to do this type of stuff for the test. I mean, you'll have to do centripetal forces and all that business, but not this type of force diagrams for the test. But I just wanted to point it out to you. MCAT and stuff like that is likely important. Okay. I think we had a few more clicker questions. I think we just have two more. You don't read that? Yes, in your book, right. Light from Dave. I want to check something right quick. I'll bring it back. Okay, let's stop at 120. 120. Okay, it is D, because well, like what we were just talking about with the Ferris wheel, that if I have a swing, a child on a swing, as it comes down to the bottom, what I have is I have a force up. This is my tension, and then I also have the weight, and so Ft minus Fw is going to equal to MAC, which is going to be positive. And so the tension, she reaches the lowest, if I want to know something about her tension, then the tension would be equal to the weight plus MAC, which isn't one of these options. So the tension is not equal to her weight. The tension is not equal to her mass times acceleration either. It actually, we have to include her weight as well. Her acceleration is not downward. All right, her acceleration is actually, you know, technical, her acceleration is upward. That's centripetal acceleration causing her to go into this circular path. Okay, we've had one similar to this, but let's try this. Rigid object, angular speed that's negative. The angular velocity vector and the angular acceleration vector are anti-parallel. That means they're same direction but are same axis but opposite directions. Let's stop at 60. 1 minute. Okay, good. It's clockwise, we know, because the angular speed is less than 0. Negative is clockwise. Clockwise means it's in the negative direction. And then because the velocity and the acceleration are opposite directions, that means it's slowing down. Remember, we just take clockwise as negative and counterclockwise as positive. So really, if you want to get technical about it, if I have a disk that's spinning in this direction, then I can use my right-hand rule. Right? That's going to be up, it's going to be positive. If I think about my clock, always clockwise this direction. And then I do my right-hand rule. My fingers go in the direction of the velocity. This has a negative velocity. Okay? So that's where those positive and negative values come from. We'll see right-hand rule a lot more next semester, so don't fret it too much right now. Okay. I close this. All right, any questions? Issues? We'll have some time next week on Wednesday to cover some more, to do some more review, sort of half the class on Wednesday. But any big nagging issues right now before we move on into Chapter 8? No? Let's move on into Chapter 8 then. But Chapter 8 will not be on the test. I think you've already had a lab, or some of you have anyway, had a lab on torque where you did the meter stick and you hung the little masses on it. How'd you like that lab? You like that lab? It's kind of fun. It's like you're a kid at the park on the seesaw, and you're trying to balance out the seesaw. So some of this will be fairly easy to you. We'll get a little bit more into torques than you do in the lab. So what is torque? What does it cause? And why is it useful to describe torque? What is torque? What is a torque? Well, it's what? Well, it's something that causes angular acceleration, right? In fact, I always like to think of a torque as an angular force. And later we'll actually draw these parallels between our linear and our rotational motion. And so you can think of a torque as an angular force. It's a force-like thing that causes motion in this angular direction. So it causes angular motion or angular acceleration. And it's useful to describe torques because, well, they describe rotation. We'll see Newton's second law here is going to extend to rotational motion. Because just like forces cause acceleration, F equals ma, torques will also cause angular acceleration. And I'm going to go ahead and write this here. We're going to use tau for our torques, and they're going to cause angular acceleration. We'll write now Newton's second law as torque equals I alpha. We'll see that later, so don't worry about it. I'll explain what those terms are, but just to throw it out there right now. And so you can think of torque then as an angular force. It's not the same as a force, but it's very similar in that it causes this acceleration, an angular force. All right, so if you say you have a crescent wrench like this, or a torque wrench, or whatever type of wrench you have, and you want to apply a certain torque to it, you'd apply a force onto the end of the wrench, and then that would be over some distance. We call this the moment arm. So you have your applied force, and then you also have your moment arm, and the magnitude of the torque is equal to the moment arm that's that distance r times the component of the force perpendicular to the moment arm. That's what that sign means, perpendicular at 90 degrees to the moment arm. And so if I look at this force as it's drawn, in fact, this isn't a very good way to use a crescent wrench, right? Like, you want, instead of having the force at an angle like this, when you're using a wrench, how do you apply the force? You apply it up in this direction? No, that's not going to do anything, right? You would apply a force in this direction. So the component of the force that's perpendicular is like this. The component that's parallel, by the way, is like that. But this force is the only one that does torque, that applies a torque. All right? You ever opened a door before? But if you open the door, imagine this door is pushed open. But if I open the door, if I push on it this way, if I pull on it like this, that opens the door, right? I'm providing a force that's perpendicular to the moment arm. The moment arm is this distance right here, 2 feet or whatever, 30 seconds. But what if I were to apply the force parallel to the moment arm? Am I ever going to shut this door? No, I'm never going to shut it because this force, even though I'm pushing on the door, doesn't provide any torque at all. So the torque is only caused by the force is only caused by a component that's perpendicular to the moment arm. We're going to write this in equation form that torque is equal to the perpendicular component F times R. But if I have an angle theta, and I want to know what this force is, F perpendicular, what is that? Did I use a cosine theta or a sine theta to find that component of the force that is perpendicular to the moment arm? Sine theta is right. So it's going to be FR sine theta. And so that gives us our sort of our generic equation for torque, FR sine theta. This comes about, if you've ever had Calc 3 or multi-vector calculus at all, don't write this down, but I'm just sort of for your own information. This comes about from the cross product of two vectors. The cross product of two vectors will take one component of a vector and multiply it by another component that's perpendicular to the first. And so if you've ever seen cross products, you know that this is the result of a cross product. Okay? Okay, so when the angle between F and R is 90 degrees, the torque, well, sine of 90 is equal to 1, and so the torque would be just FR times 1 when it's 90 degrees. And if the force is in this direction, where theta equals either 0 or 180 degrees, we'll call it 180, then the torque is equal to FR times sine of 180. The sine of 180 is 0, so the torque would be 0. All right? Try to open a door. Like, go to your class next time, or try to close the door, I guess, and push on the door in that direction. And somebody asks you what you're doing, you say, I'm just trying to have a different angle for my torque and see if it works. But it doesn't work, because you're now parallel to the moment arm. That just doesn't work. Okay? All right, the SI unit for torque is the Newton meter. And just to remind us, a Newton is a kilogram meter per second squared, right? That's mass times acceleration. And then we add in that other meter. So a Newton meter is the same as kilogram meter squared per second squared. And that just comes from this expression. The sine of an angle doesn't have any units, so I just don't worry about that. Clockwise torques are negative. Counterclockwise torques are positive. Okay? In order to have static or equilibrium conditions, you have to have two criteria. And if you're going on engineering, I know that none of y'all are, but if you go on into engineering, you take whole classes on this. It's called statics or dynamics. But you have to meet these two criteria. You have to say that the sum of the forces is equal to 0. Because in order to have static or equilibrium conditions, you want the acceleration to be 0. And so the sum of the forces has to be 0. And then also, you don't want the thing to be rotating either. Because you don't want your building to just start rotating, right? That you've just built. So you also say that the sum of the torques equals 0. And then that condition is set by that our alpha is equal to 0. So if you want to have static or equilibrium conditions, we did this before in chapter 4. But now we can also say that in order for these equilibrium conditions to be met, for something to be not moving, then the torques have to add up to 0 too. Okay, just a few more minutes. I know you are getting sleepy. Some of you are sleepy. It's because the lights are down, right? Is that the problem? Because this side of the class, look, they're all wide awake. But this side of the class, you're like all drooping. Eyelids drooping down. Let's try this. Here you want to calculate the net torque. So a couple of things you want to do here is first ask yourself, what is my axis of rotation? And here we're rotating about the axis C. So we're rotating about this point. And then for each force, you want to calculate the torque. And remember, torque is Fr sine theta. Being careful of your signs, not the trigonometric function, but of your plus and minus sign. Because some of these forces will cause positive torques, and some of them will cause negative torques. Positive are counterclockwise, negative are clockwise. Some of the forces might not cause any torque at all. You know, with the door, you can change your angle, but you can also change your moment arm. You think I'd ever be able to close the door if I pushed it here? Am I going to ever push the door here? No, because my moment arm is 0, and that means that my torque is 0. About a third of you have it right. Now about 16 of you have it right. Each of these forces will produce a torque, or some of them might not at all. And you want to add up those torques. Just take the sum of them. I mean, we could finish this chapter by next Friday. We could. We'll hold off. No rush. What's the rush? What's the hurry? We'll get there eventually. I'm going to see you next year anyway. Next spring. We're in this thing for the long haul. All right? Let's stop at 3:15, okay? 3:15. Okay. What'd y'all tell her? You didn't tell her the right answer. Oh. No, stop. Okay, C is the right answer. Okay, so first of all, when you come upon one of these problems, and you will on the test, exam 4 that is, you need to ask yourself which of these provide no torque at all. Which of them provide no torque? The 25, 30, or 20? 30, right? And why the 30 doesn't provide any torque at all? Right, it's at the center. It's at the axis of rotation. So R equals 0 for this one, so it provides no torque at all. I'll just get rid of it. And then ask myself, which of these provides negative and which provides positive torque? Well, if I imagine my rod here, this force is going to pull it down and make it go in this direction. And so what's that? That's clockwise, right? Or no, counterclockwise, rather. So this will provide a positive torque, and this one's going to cause it to go in this direction. So that's clockwise. So I have a positive torque from the one on the left and a negative torque from the one on the right. So I'm going to get my signs all sorted out, right? I'm going to call this torque 1, and I'll call that torque 2. And so the sum of the torques will be torque 1 minus torque 2. And by the way, it's not always going to be the one on the left will be positive and the one on the right will be negative. It's not always that way. I could just switch the direction of these forces, right? If I move this one up here, then that would be a positive torque, not a negative torque, because it would cause counterclockwise motion. Torque 1 is Fr sine theta, 25 times the moment arm, which is 2, times sine of 45, minus 20 times 2 sine of 20. And the answer is positive 22 Newton meters, which is going to be counterclockwise. All right, we'll get more practice with that. Don't worry about it if you didn't get it just now. You'll get it before we leave. Y'all have a great weekend. Soccer game at 3 today, I think.